Right now, beyond the last known planet of our solar system, something massive is orbiting our sun in complete darkness. A cold, invisible world, larger than Earth, buried so deep in the outer solar system that darkness swallowed it entirely. Scientists call it Planet 9. Every calculation points to the same conclusion. It exists. Distant objects past Neptune are being pulled, bent, dragged off course by something enormous and unseen. Every telescope we aimed into that void returned nothing. Then James Webb arrived. Unlike everything before it, Webb hunts in infrared. It sees cold, it sees dark, it sees hidden. What it is tracking there could finally give scientists the answer that has escaped every telescope before it. Before we dive in, if you love exploring these kinds of deep space videos, a simple like or subscribe really helps this channel reach more curious minds like yours. Now, let everything soften, and together we drift into space. For nearly a decade, astronomers have been working with a specific and unusual problem. The orbits of small icy bodies at the far edge of our solar system appear to be influenced by something with mass, with gravity, with a measurable gravitational effect on the objects around it. That something has never been directly observed. No telescope has captured its light. No spacecraft has crossed its path. What it is, whether it exists at all, and what finding it would mean for our understanding of the solar system, that is what this story is about. And it begins much earlier than most people realize. The idea of a hidden planet beyond the edges of what we can see is not new. Astronomers have been here before, more than once. In the mid-19th century, scientists noticed something deeply unsettling about the planet Uranus. Its orbit was wrong. Not dramatically wrong, but persistently, stubbornly, measurably wrong. Uranus kept drifting slightly from where Newtonian physics said it should be. The numbers were precise. The instruments were reliable, the discrepancy was real, the response was extraordinary. Rather than doubt the physics, astronomers proposed a solution. Something unseen was out there, pulling on Uranus with gravity strong enough to shift its orbit. A hidden planet. And in 1846, using only mathematics, no telescope, no photograph, nothing but pure calculation, the French mathematician Urbain Le Verrier predicted where that hidden planet would be. Observers pointed their instruments at the coordinates, and there it was, Neptune. Discovered not with light, but with logic. That moment changed everything. It established a template that would echo through astronomy for the next 2 centuries. If an orbit misbehaves, something is pulling on it. Find the pull, find the planet. Decades later, a wealthy Bostonian astronomer named Percival Lowell became convinced the story wasn't finished. Even with Neptune accounted for, Lowell believed the orbits of Uranus and Neptune still carried faint anomalies, tiny deviations too small to see easily, but too persistent to ignore. He was certain another planet existed beyond Neptune. Something even further out, even more massive, pulling on the known giants from a distance no one had yet measured. He called it Planet X. The X was not a Roman numeral. It was a variable, an unknown, a blank to be filled in. In 1906, Lowell began a systematic search from his observatory in Flagstaff, Arizona. He employed a team of human computers, actual human beings, led by a mathematician named Elizabeth Williams, who performed the calculations by hand, predicting likely sky positions for this unseen world. He then photographed those regions of sky, searching for any faint dot that moved. He searched for a decade. He found nothing. Lowell died in 1916, his great quest unfulfilled, but his observatory continued, and in 1929, a 22-year-old farm boy from Kansas named Clyde Tombaugh arrived at Lowell Observatory with no formal astronomy degree, a passion for the night sky, and a talent for careful observation. His assignment was simple in description and brutal in execution. Search the sky systematically section by section, for any moving object. On February 18, 1930, Tombaugh was comparing two photographic plates of the same star field taken several weeks apart, a technique called plate blinking, where alternating rapidly between the two images creates a flicker effect that reveals any object that has moved. And something moved, a faint, tiny dot, shifting against the fixed backdrop of the stars. The announcement reached the world on March 13, 1930, the anniversary of Percival Lowell's birthday. The discovery was celebrated as the find of the century. The 9th planet had been found. They named it Pluto. Here is where the first great unravelling begins. Scientists were confident Pluto was the planet X Lowell had predicted. The orbital position was close enough to his calculations to feel like confirmation, and for 76 years, Pluto held its title, the 9th planet in our solar system. But the numbers never quite worked. Almost immediately after its discovery, astronomers began to suspect that Pluto was far too small, far too light, to actually be responsible for tugging on the giant planets. Pluto turned out to be smaller than Earth's moon, far smaller. Its gravitational influence on Neptune or Uranus was, effectively, nothing, like trying to shift an ocean liner with a marble. Then came the decisive blow. In 1989, the Voyager 2 spacecraft swept past Neptune and measured its mass with new precision. When scientists recalculated the orbits of Uranus and Neptune using the corrected mass, the anomalies that had launched the whole century-long Planet X search simply vanished. They were never real. They had been measurement errors all along. The problem Percival Lowell had spent his life trying to solve had never existed. And on August 24, 2006, the International Astronomical Union voted to reclassify Pluto. Not a planet. A dwarf planet, the largest member of a vast belt of icy objects beyond Neptune called the Kuiper Belt. The number of planets in our solar system dropped from 9 to 8. For the first time in modern astronomy, the solar system felt finished, complete, accounted for. That feeling did not last long. Something began to surface in the data, not from a grand telescope campaign, not from a targeted search, but from the accumulated observations of a small population of objects in the outermost reaches of the solar system, bodies called extreme trans-Neptunian objects. To unpack that term, these are small, icy worlds orbiting the Sun at distances so extreme that Neptune, itself one of the outermost planets, is practically a neighbour by comparison. What scientists noticed was this: 6 of these distant objects, with orbits ranging from 150 to over 500 times the Earth-Sun distance, were aligned. Not exactly in the same place, but pointing in the same direction. Their orbits clustered together in a way that pure chance could not easily explain. The probability that 6 independent objects would align like this by random orbital drift? Astronomers calculated it at roughly 0.007%, meaning if you drew a billion versions of the outer solar system in a computer simulation without any hidden planet, almost none of them would produce this pattern. Something was shepherding these objects, organizing them, holding them in alignment through gravity. On January 20th, 2016, 2 astronomers at the California Institute of Technology, Konstantin Batygin and Michael Brown, published a paper in the Astronomical Journal that would reignite the entire conversation. Their argument was not based on a telescope image. It was not a photograph. It was mathematics. Running thousands of computer simulations, Batygin and Brown showed that a single undetected planet, the right mass, the right distance, the right orbit, could explain all of the clustering they observed. And the portrait that emerged from those simulations was striking in its specificity. This hypothetical world, which they called Planet 9, would have a mass somewhere between 5 and 10 times the mass of Earth. 5 to 10 times. Our entire planet, with all its oceans and continents and iron core, would fit inside Planet 9 somewhere between 5 and 10 times over. Its orbit would stretch between roughly 400 and 800 astronomical units from the Sun. 1 astronomical unit is the distance from the Earth to the Sun, about 93 million miles, or 150 million kilometers. Neptune, farthest known planet, orbits at about 30 of these units. Planet 9, if it exists, would orbit at somewhere between 13 and 27 times farther than Neptune. At its closest approach to the Sun, it would be about 37 billion miles away. At its most distant, it may wander as far as 74 billion miles, a distance so immense that the Sun would appear as nothing more than the brightest star in a black sky, giving no more warmth than a distant campfire glimpsed across a dark field. And its orbital period, the time it would take to complete 1 full journey around the Sun, Batygin and Brown estimated at somewhere between 10,000 and 20,000 years. To hold that number for a moment, 10,000 years ago, human civilization was just beginning. The wheel had not been invented. Writing did not exist. Agriculture was new. If Planet 9 began a single orbit around the Sun at the dawn of human civilization, it would still be travelling that same orbit right now, and it would be less than halfway through. Batygin himself was careful. Publicly, he acknowledged the weight of what the mathematics implied, while refusing to overreach what the mathematics actually proved. As he said at the time, until Planet 9 is caught on camera, it does not count as being real, and there are genuine reasons for that caution. In 2020, 2 large surveys, the Outer Solar System Origin Survey and the Dark Energy Survey, together catalogued hundreds of trans-Neptunian objects and concluded that, once observational biases were accounted for, they found no clear evidence of the clustering that Planet 9 was supposed to explain. Samantha Lawler, one of the study's authors, stated that the Planet 9 hypothesis, as proposed, did not hold up to the larger sample sizes now available. So the debate is real, the evidence is contested. 2 groups of scientists looking at the same solar system are reaching different conclusions. That tension is not a weakness in science. That tension is exactly how science works. One side says the alignment is too significant to ignore, the other says the data is too incomplete to trust. Both sides are doing exactly what they should, and neither has yet closed the case. What makes this uniquely difficult is not the science. The mathematics of Planet 9's orbit is well understood. The physics of gravitational shepherding is not in dispute. What makes this uniquely difficult is something far more fundamental. Planet 9, if it exists, is not a star. It produces no light of its own. At those distances, the sunlight falling on its surface would be so dim, so faint, that its reflected glow would be almost nothing. Finding it would be like trying to spot a dark stone sitting at the bottom of a lake on a moonless night from the far shore. That is the challenge, and it raises a question that has haunted the search for over a decade. If Planet 9 is out there, if an entire world 5 to 10 times the mass of our own is tracing a silent arc through the outer darkness, what kind of instrument could possibly detect it? What kind of telescope could peer far enough, deep enough, sensitively enough into that freezing void to find a planet that has never once caught the light? That question turns out to have a very specific answer, and it requires understanding something about the way cold, distant objects reveal themselves. Not in visible light at all, but in an entirely different kind of radiation that our eyes were never built to see. Finding a cold, dark object at the very edge of our solar system is not simply a matter of pointing the right telescope in the right direction. The problem is far deeper than that. And understanding it changes everything about how you think the search must be conducted. Most of us carry an intuitive picture of how telescopes work. You point one at the sky, the light from a distant object travels through the lens, and something bright appears. A planet glows, a star burns, a moon reflects. The telescope collects the light, and the object is found. But that picture only holds when there is light to collect. Planet 9, if it exists, emits almost none. At distances of 400 to 800 astronomical units from the Sun, the sunlight falling on its surface would be so diluted, so ferociously reduced by distance, that the planet would reflect back little more than a ghost. And what faint energy it does radiate on its own, the residual warmth left over from its formation billions of years ago, would not emerge as visible light at all. At temperatures estimated around 47 degrees above absolute zero, colder than any place on Earth, colder than the dark side of Pluto, the planet would glow almost entirely in infrared, in heat, in a form of light the human eye was never built to see. This is where the search becomes not just a challenge of distance, but a challenge of perception itself. To understand why this matters, we need to briefly understand what infrared radiation is, because it is the key that unlocks the entire search. Visible light is only a narrow slice of a much broader spectrum of electromagnetic radiation. Think of the full spectrum as a piano keyboard stretching across an entire city block. The notes our eyes can hear, red, orange, yellow, green, blue, violet, occupy a tiny stretch of keys near the middle. Infrared sits just to the right of red, in the lower octaves. The notes are longer, slower, warmer, and every object in the universe that has any heat above absolute zero emits infrared radiation. The warmth from a mug of coffee, the heat escaping through a poorly insulated window on a winter night, the faint residual warmth of a world that formed 4.5 billion years ago and has been slowly cooling ever since. A cold body at the edge of the solar system would be essentially invisible in regular light, but in infrared, given a sensitive enough instrument, it would glow, faintly, but measurably. The challenge is building or finding the right instrument and then knowing where to point it. In 2009, NASA launched a space telescope called WISE, the Wide Field Infrared Survey Explorer. Using a 40-centimeter mirror, about the size of a large dinner plate, WISE scanned the entire sky in 4 infrared wavelength bands over 10 months. By the standards of infrared all-sky surveys at the time, it was extraordinary. Scientists catalogued hundreds of thousands of new objects. WISE found brown dwarfs, objects too small to ignite as stars but too large to be planets, lurking just a few light years from our own sun. Objects no one had ever known existed, practically in our cosmic neighborhood. And yet, in March of 2014, NASA announced that WISE, after its exhaustive survey, had found no evidence of Planet 9. Scientists were not entirely surprised. WISE was powerful for its time, but it carried a fundamental limitation. For a planet orbiting at the outer edges of its predicted range, 800 astronomical units or beyond, the infrared signal would be too faint, too cold for WISE to reliably detect. The telescope had the right kind of eyes, but not enough of them. Its primary mirror, 40 centimeters across, collected light from the sky the way a small bathroom window collects daylight, sufficient for certain tasks. But for hunting something as faint and distant as Planet 9 near the far end of its orbit, the window was simply too small. What WISE did do, crucially, was narrow the search. By ruling out any large, warm object close to the Sun's vicinity, it constrained where Planet 9 could not be. The search area shrank, the candidates narrowed, and in doing so, WISE pushed the likely position of Planet 9 further out, deeper into the dark, and harder to reach. Here is something remarkable to consider. Even if Planet 9 is out there right now, in every photograph that has ever been taken of its region of sky, its image likely already exists somewhere in an archived data set, hidden, unrecognized, buried in the noise. The reason it hasn't been spotted is subtle and worth understanding. At distances of 400 to 800 astronomical units, a planet moves across the sky with almost imperceptible slowness. An object at those distances takes between 10,000 and 20,000 years to complete a single orbit. Spread that motion out over a single year, or even a decade, and the shift against the background stars becomes tiny. Not zero, but tiny enough that in any single photograph, Planet 9 would look identical to a distant galaxy or a faint background star, indistinguishable, lost in the noise. Finding motion at this scale requires a different approach entirely, not a single photograph, not even a series taken over weeks. The only way to reveal a slowly drifting point of light hidden among billions of static ones is to compare images taken years apart, and to look for something that has shifted, however slightly, between them. Picture looking at two photographs of a vast crowd of people taken 6 months apart. Nearly everyone has stayed in place, but one person somewhere in the crowd has moved 3 steps to the left. If you can somehow overlay those two photographs and highlight the difference, that one person becomes visible. That is exactly the logic astronomers use when hunting for Planet 9 in archival data. The most powerful evolution in this approach is a technique called shift stacking. Astronomers Milena Rice and Gregory Laughlin at Yale University developed and applied it to transform the search for faint outer solar system objects. The logic works like this. A single telescope image of Planet 9's likely sky position would show its signal far too faint to detect, buried beneath the noise of the camera's own electronics and the dim glow of background light. But if you take dozens or hundreds of images of the same region of sky over time, and then shift each image slightly along the path that a planet at a certain distance and speed would be expected to travel, you can stack all those shifted images on top of each other. The noise, being random, cancels out. The signal from the moving object, because every shifted image has placed it in the same position, reinforces itself. Suddenly, something that was invisible in any single frame becomes visible in the combined image, like a message that only appears when you hold many transparent sheets against a light. As Rice put it directly, you really can't see them without using this kind of method. If Planet 9 is out there, it's going to be incredibly dim. Researchers tested this technique first by successfully recovering the signals of 3 known distant solar system objects, Sedna among them, from telescope images where those objects appeared far too faint to identify by any other means. The test worked. The objects were found exactly where they were supposed to be. The researchers then applied the same technique in a blind search and identified 17 new candidate objects in the outer solar system. None of those candidates were large enough to be Planet 9, but the principle was proven. The method works. The limitation? Running a shift-stacking search across the entire predicted parameter space for Planet 9, all possible distances, all possible sky positions, all possible orbital angles, requires an almost incomprehensible amount of computing power. Each possible orbital path must be tested separately. Each test requires the full dataset to be reprocessed. The number of possible paths is enormous. To search the full sky this way demands not just clever algorithms, but computing resources on a scale that only became practical with modern supercomputing. This brings us to what astronomers call the parameter space problem. It is one of the most honest admissions in the entire Planet 9 story. Even if we know roughly where Planet 9 should be, somewhere in a predicted arc of sky, at a distance of roughly 400 to 800 astronomical units, roughly covers an enormous amount of territory. The sky spans 360 degrees in every direction. The full area of uncertainty in Planet 9's predicted sky position, after accounting for all the orbital modelling, still covers billions of square degrees. More than half the entire celestial sphere remains a plausible hiding place. Now imagine you are searching a haystack, not the size of a room, but the size of a city, and the needle you are looking for is not just small, it is also invisible in ordinary light, moves only a few steps over the course of a decade, and is currently somewhere beyond 37 billion miles away. That is the parameter space problem. Not impossibly large, but large enough that every telescope survey completed so far has only eliminated a fraction of it, And this is where the Vera C. Rubin Observatory enters the story in a way that has genuinely changed the mood among astronomers searching for Planet 9. Built atop Cerro Pachón, a mountain in northern Chile rising 2,682 meters, or 8,799 feet above sea level, Rubin is not simply a large telescope. It is a fundamentally different kind of astronomical instrument. Its primary mirror spans 8.5 meters, roughly the width of a two-story house from floor to ceiling, and behind that mirror sits the largest digital camera ever built for astronomy, 3.2 gigapixels, 3.2 billion individual pixels. A single image from Rubin's camera covers a patch of sky 45 times larger than the full moon. Every single night, the observatory surveys nearly the entire visible southern sky, generating around 20 terabytes of new data, the equivalent of filming 4,000 hours of high-definition video, every 24 hours. What makes Rubin especially powerful for this search is not just the size of its camera, it is the repeatability. Every few nights, the observatory returns to the same patches of sky, compares the new image to the previous one, and flags anything that has moved or changed, automatically, in real time. Rubin will do this for 10 years, building a decade-long time-lapse record of the entire southern sky that no previous survey has ever approached. Scott Shepard of the Carnegie Institution for Science, one of the researchers who first identified the orbital clustering that sparked the Planet 9 hypothesis, was direct about what Rubin represents. Vera Rubin is our best bet to find it in the next few years, probably, he said. It's going to turn over more rocks than anyone has turned over before. If Planet 9 exists within its detection range, he estimates Rubin has roughly a 70 to 80% chance of finding it. Michael Brown, the Caltech astronomer who, alongside Konstantin Batygin, proposed Planet 9 in the first place, was equally unequivocal. If you were to hand me a big wad of cash and say, go build a telescope to either find Planet 9 or find the best evidence possible for Planet 9, I would probably go and build the Vera Rubin Observatory. It really is a telescope perfectly suited for making the next step. In June of 2025, Rubin released its first public images. In just 10 hours of observation during that initial test, it discovered 2,104 previously unknown asteroids, 2,000 new solar system objects, in a single night of work. The survey has now begun. The data is accumulating, but here is where the story does not simply end with confidence. Rubin surveys in visible light. It is an optical telescope, extraordinarily powerful, but fundamentally limited to the same kind of radiation human eyes evolved to detect. And Planet 9, if it exists near the far end of its orbit, the cold, dark region where it likely spends the vast majority of its 10,000-year journey, would be almost entirely invisible to optical instruments. The reflected sunlight reaching it at 800 astronomical units would be so reduced that the planet might fall just below Rubin's detection threshold. Not found, not ruled out, simply unresolved. To push past that barrier, to look for Planet 9 not by the faint sunlight it reflects, but by the even fainter infrared warmth it radiates on its own, requires something else entirely. Something that doesn't just see farther, but sees differently. A telescope built not for light, but for heat, for cold, for the invisible signature of a world that has been slowly cooling since before our sun had planets. That telescope exists, and its arrival changed what was possible in this search in ways no one had quite anticipated. That telescope is the James Webb Space Telescope, and understanding why it matters for this search requires understanding something that most people have never thought about, something that changes the way you see the entire problem. Almost everything we know about the universe, we know because something was bright enough to be seen. Stars burn, galaxies glow, even planets like Jupiter and Saturn reflect enough sunlight that a patient observer with a good telescope can find them. The history of astronomy is, in one sense, the history of learning to see things that are bright. But Planet 9, at its estimated distance, would not be bright in any conventional sense. At 400 to 800 astronomical units from the Sun, distance is so vast that the Sun's light arrives attenuated nearly beyond recognition. The planet would reflect almost nothing back toward us. Any telescope searching for it in visible light is, effectively, hunting for something that barely shines. And that is why every previous search has ultimately run into the same wall. What changes the equation is this: every object in the universe that has any temperature above absolute zero emits energy, not necessarily as light, but as heat, as infrared radiation. A cold body at the edge of the solar system may be essentially invisible to human eyes and optical telescopes, but to an instrument tuned to the right infrared wavelengths, it would glow, faint but real. James Webb was built precisely for that kind of seeing. Webb launched on December 25, 2021, and travelled to a location called Lagrange Point 2, a gravitationally stable point in space about 1.5 million kilometres, roughly 930,000 miles from Earth. That's about 4 times the distance from Earth to the Moon. Far enough that Earth's own warmth cannot contaminate its readings. Far enough that its sunshield, a 5-layer, house of cards structure measuring 22 metres long and 12 metres wide, roughly the footprint of a tennis court, can permanently point away from the Sun and keep the telescope in perpetual, stable cold. Webb's primary mirror spans 6.5 metres across, 21 feet, assembled from 18 hexagonal gold-plated segments that unfolded in space like the petals of an extraordinary flower. That mirror gives Webb a light-collecting area of about 25 square metres. To hold that comparison, WISE, the infrared survey telescope that searched for Planet 9 a decade ago, carried a mirror 40 centimetres, 16 inches, across. Webb's mirror is more than 260 times larger in collecting area. The difference between those two instruments is not a matter of degree. Looking for Planet 9 with WISE was like trying to hear a whisper from across a city with a standard telephone receiver. Webb arrives with something fundamentally different, an instrument capable of detecting objects up to 100 times fainter than the Hubble Space Telescope could ever manage. And unlike Hubble, Webb was not designed to see invisible light. Webb operates entirely in the infrared, from the long red end of visible light all the way through mid-infrared wavelengths that no human eye can detect at all. Before Webb can matter to the Planet 9 story, we need to understand a piece of physics that is both simple and quietly remarkable. Every object emits electromagnetic radiation, light in its broadest sense, at a peak wavelength that depends on its temperature. Hotter objects peak at shorter, more energetic wavelengths. The surface of the Sun, at around 6,000 degrees, peaks in visible yellow-green light. That's why sunlight looks the way it does. A cooler red star peaks further into orange and red, and an object that is truly cold, hundreds of degrees below the coldest place on Earth's surface, peaks deep in the infrared. Planet 9, based on current theoretical models, would have a surface temperature of approximately 47 kelvins. To understand how cold that is, water freezes at 273 kelvins. Liquid nitrogen, used to flash freeze biological samples in laboratories, boils at 77 kelvins. Planet 9, at 47 kelvins, would be colder than liquid nitrogen, colder than anything in any laboratory you have ever visited. At that temperature, the planet's thermal emission, the energy it radiates from the heat of its own formation, cooling over 4.5 billion years, would peak at wavelengths in the mid-infrared range. Not near infrared, not visible, mid-infrared, wavelengths between roughly 10 and 60 microns, invisible to every instrument that preceded Webb. And this is where Webb carries an advantage that no previous telescope has ever possessed. Among Webb's 4 scientific instruments, one stands apart for this search: MIRI, the mid-infrared. Instrument is a camera and spectrograph that detects wavelengths between 5 and 28.5 microns. That range sits precisely where a cold, distant world like Planet 9 would emit most of its detectable radiation. But detecting mid-infrared requires the instrument itself to be extraordinarily cold. Any warmth in the detector would create its own infrared glow, drowning out the faint signals from distant objects the way a room full of candles makes it impossible to see a single match flame from across the street. So Miri cannot simply be cold. Miri must be kept at approximately 7 kelvins, 7 degrees above absolute zero, minus 266 degrees Celsius, minus 447 degrees Fahrenheit. This is colder than any natural object in our solar system. To achieve it, Miri carries its own dedicated cryogenic cooling system, an additional mechanical refrigerator built into the telescope solely to maintain Miri at this temperature. Webb's other instruments rest at around 40 kelvins, already extraordinarily cold. Miri is 33 degrees colder still. The engineering required to keep a sensitive detector at 7 kelvins in a spacecraft traveling through deep space is, by any measure, a remarkable human achievement. Right now, as you read this, Miri is operating at that temperature, 1,000,000 miles from Earth, held in permanent shade, cooled to within 7 degrees of the coldest possible state of matter, and scanning the universe in wavelengths no previous observatory could reach. The contrast with WISE is worth sitting with for a moment. WISE surveyed the entire sky rapidly, covering vast areas with a 40-centimeter mirror and a fixed infrared sensitivity. Its strength was breadth. It covered enormous sky area quickly. Its limitation was depth. It could not collect enough light to detect the faint, cold signal of a planet at the extreme outer limits of the solar system. Webb works in the opposite direction. Webb's strength is depth. With its 6.5-meter mirror, cooled instruments, and unparalleled sensitivity, it can stare at a small patch of sky and detect objects hundreds of times fainter than WISE ever could. But Webb's field of view is small, much smaller. To compare, WISE swept across the sky in broad strokes, imaging enormous regions at once. Webb, pointed at the same region, would see a tiny fraction of the same area, but with dramatically greater sensitivity and detail. WISE was a wide net. Webb is a precision instrument. One cannot replace the other. They serve fundamentally different functions. This creates an immediate strategic problem. You cannot simply point Webb at the sky and tell it to search for Planet 9. Without knowing where to look, you could spend decades of observation time and never cross the right patch of sky. Webb is not a survey telescope. Webb is a discovery engine, but only if you can first narrow down where to aim it. This is where the mathematical work of the past decade becomes essential. Since Batterjin and Brown published their hypothesis in 2016, teams of astronomers have been running increasingly sophisticated simulations, computer models that account for Planet 9's predicted orbit, the gravitational architecture of the outer solar system, the known positions of the extreme trans-Neptunian objects whose clustering started this whole story, and using those simulations to build what researchers call parameter maps. A parameter map is exactly what it sounds like: a probability distribution overlaid onto the sky, telling you which regions are most likely to contain Planet 9, given everything the mathematics currently suggests. These maps do not guarantee a location, but they concentrate the possibilities into preferred regions, areas where, if Planet 9 exists, and if the orbital models are correct, the planet is more likely to be found. Astronomers know, for instance, that Planet 9 probably spends most of its orbital time near its farthest point from the Sun, what is called aphelion. This is simply a consequence of orbital mechanics. An object on a highly elongated path moves slowest when it is furthest away, spending the majority of its time at the distant end. An orbit that takes 10,000 to 20,000 years to complete would see the planet spend perhaps 8,000 or more years of every cycle near its outer limit. The probability map tilts strongly toward the aphelion region. Combined with constraints from existing survey data, what regions have already been searched and ruled out, a picture emerges of which patches of sky deserve the closest, deepest, most sensitive attention. Webb, with its unmatched infrared sensitivity and MIRI's cold body detection capabilities, becomes the natural instrument to point at those prioritized zones. Not blindly, not broadly, but with surgical precision, staring at the most likely regions for the hours or days of integration time required to push its sensitivity to its outer limits. But here is where the problem deepens in a way that surprises most people. Even if Planet 9 is sitting in Webb's field of view right now, even if its thermal glow is falling onto MIRI's detectors at this very moment, finding it in the data is far from straightforward. At mid-infrared wavelengths, the sky is not empty. The background is densely populated. Distant galaxies emit prolifically at these wavelengths. Clouds of interstellar dust in our own Milky Way glow with infrared emission. Faint stars contribute signatures that overlap with what a cold, distant planet would produce. Any single mid-infrared image of a suspected sky region contains thousands of sources, and almost all of them are not Planet 9. Separating the genuine candidate from this crowded background requires a combination of tools. First, cross-referencing with existing catalogues to remove known stars, galaxies, and asteroids. Second, looking for spectral signatures consistent with a cold, large body rather than a star or galaxy. Third, and most critically, looking for motion. A background galaxy does not move. A background star over years moves only imperceptibly. But a planet, even at 400 to 800 astronomical units, moves across the sky in a way that, given images taken years apart, can in principle be detected. This is how astronomers have pursued the deepest archival searches, not just pointing telescopes and hoping, but comparing images taken at different epochs, separated by years or decades, hunting for the one source in thousands that has shifted its position against the otherwise static backdrop of the cosmos. Jim Green, former director of NASA's Science Mission Directorate, was among the first senior NASA officials to publicly express optimism that Webb could detect Planet 9 if the planet falls within a region accessible to targeted observations. And Webb has already proven, in its first years of operation, that its solar system science capabilities surpass everything that came before. Webb has mapped the atmospheres of distant moons. It has studied the chemical composition of Kuiper belt objects in detail that ground-based telescopes cannot approach. Webb has observed the faintest, coldest objects in our solar system's outer reaches with a clarity that would have been impossible a decade ago. The question, as of now, is not whether Webb is sensitive enough. The question is whether the orbital models are accurate enough to tell us where to look, and whether, somewhere in the archive of accumulated infrared observations, some from Webb, some from older surveys, a signal has already been recorded that no one has yet recognized for what it is. That possibility is not abstract. Scientists have gone back to older infrared surveys, data sets collected before Webb ever launched, surveys that pointed at large regions of sky for entirely different scientific purposes, and asked a different question. Not, was Planet 9 in the field of view? But rather, is there anything in these archives that moved? Anything that appeared in one survey and then, decades later, in another survey of the same region, appeared in a slightly different position? The answer that emerged from some of those searches is one of the most quietly unsettling developments in this story. Something moved, not a confirmed planet, not a verified discovery. But in multiple archival datasets, researchers found candidate infrared sources, faint, cold, consistent with the predicted profile of Planet 9, that appear to have shifted between surveys separated by years or decades. Sources that were not background galaxies. Sources that were not known asteroids. Sources that, if they are real, and if their motion is real, would be consistent with a large, cold world orbiting at approximately the distance Planet 9 is predicted to inhabit. Whether those candidates are real, whether they represent a true detection, a false alarm, or something else entirely, depends on one thing above all else: follow-up. Targeted, precise, deep observations. The kind of observations that only a small number of telescopes in the world are capable of performing. One of those telescopes is Webb. Something moved. 2 words. Quiet. Almost understated. But in the context of the search for a hidden planet at the edge of our solar system, those 2 words carry the weight of decades of failed attempts, frustrating near misses, and the slow, patient accumulation of evidence that may finally be pointing somewhere real. Before we follow that thread, we need to understand something more deeply, something that seems straightforward but is actually remarkable. In the outer solar system, at the distances where Planet 9 is predicted to orbit, the concept of motion works in a way that requires careful thought. Because detecting that something has moved, something hundreds of astronomical units away, is not like watching a car pass by a window. The movement is so slow, so subtle, so compacted by distance, that to a single observer at a single moment, the object might as well be frozen in space. Motion at these scales only becomes visible when you hold 2 images side by side, and measure the gap between where something was and where it is now, separated not by seconds, not by minutes, but by years, sometimes by decades. To understand why this is true, picture this. Imagine standing in a large open field and watching a car drive slowly across the landscape, perhaps a mile, about 1.5 kilometers away. The car's movement is obvious, easy to track. Now imagine the same car but 10 miles, 16 kilometers away. Its motion becomes harder to notice. At 100 miles, even a fast car would appear nearly frozen against the horizon. Planet 9, if it exists, orbits at a distance somewhere between 500 and 800 astronomical units, between 46 and 74 billion miles, or between 74 and 119 billion kilometers from the Sun. At that distance, the planet traces its orbital arc across the sky at a rate of roughly 3 arc minutes per year. An arc minute is 1/60th of a degree, a unit of angular measurement so small that the naked human eye cannot resolve it. For comparison, the full moon spans about 30 arc minutes across the sky. Planet 9, in an entire year, would drift across the sky by a distance equivalent to roughly 1/10 the diameter of the full moon. In a single day, the movement would be unmeasurably small to any normal instrument. In a week, still invisible to most cameras. Only when observations taken years apart are compared does the shift become detectable, and even then, only barely. This is why the archival approach, mining old data sets for faint, slowly drifting signals, is not just clever. It is among the only viable strategies available to us right now. 2 infrared space telescopes, separated by 23 years, provided the raw material for the most compelling observational candidates yet found. The first was IRAS, the Infrared Astronomical Satellite, launched in 1983. IRAS surveyed the entire sky in far infrared wavelengths over roughly 10 months, creating the first comprehensive infrared map of the full celestial sphere. It detected hundreds of thousands of sources, infrared-emitting objects that had never been catalogued before. But IRAS operated at the limits of the technology available in the early 1980s. Its angular resolution was modest. Its sensitivity, by modern standards, was limited. And critically, IRAS made only a single pass. It could not track motion because it observed each region of sky only briefly before moving on. The second survey was Akari, a Japanese infrared space telescope launched in 2006 and operated by the Japan Aerospace Exploration Agency with participation from the European Space Agency. Akari surveyed the same sky from its far-infrared instruments, building a second all-sky map 2 decades after IRAS had built the first. On its own, Akari's data set was valuable but incomplete. Alongside IRAS, with a 23-year gap between them, it became something far more powerful, a before and after snapshot of the infrared sky, separated by enough time that a slowly moving planetary body at extreme distances would have visibly changed its position between the two observations. 23 years may sound like a long wait, but at 500 to 700 astronomical units from the Sun, a planet moving at the pace required by its orbital mechanics would shift by roughly 42 to nearly 70 arc-minutes over that time window. That is a range just large enough to be detectable, just large enough to stand out, if you know what to look for and if you apply the right filters. In April 2025, a team of researchers led by Terry Long Fan of National Tsinghua University in Taiwan, working alongside colleagues from Japan and Australia, published a study in the publications of the Astronomical Society of Australia that methodically applied this approach. Their method began with prediction. Before searching for anything, they calculated what Planet 9 should look like in these surveys, what brightness in which infrared wavelength bands, at what expected rate of angular motion, given a range of possible masses between 7 and 17 Earth masses, and distances between 500 and 700 astronomical units. These predictions became the filters, the specific criteria against which any candidate source had to be measured. They then systematically cross-referenced sources appearing in the IRAS catalogue with sources appearing in the Akari catalogue, looking for pairs of detections separated by the right angular distance, the distance consistent with the calculated motion a Planet 9-like object would cover in 23 years. They started with millions of catalogue entries, after applying flux requirements, positional constraints, and rejecting all known stars, galaxies, and asteroids through 9 separate reference catalogues. 13 candidate pairs remained, 13 objects that were in the right place, with roughly the right brightness, separated by roughly the right distance between the IRAS and Akari datasets. Then came the visual inspection. Each candidate was examined directly in the survey images, not just matched between catalogues, but actually looked at. Could the source be identified in its expected position in both images? Did it appear in IRAS, but not at the same coordinate in Akari? Did a corresponding source appear in Akari at the shifted position, but not in the corresponding IRAS image from 23 years earlier? One candidate passed every test. The object that emerged from this process carries a profile that matches the predictions for Planet 9 with a precision that no previous observational candidate had achieved across multiple independent surveys. In the IRAS data from 1983, a faint infrared source appears at a specific sky position. 23 years later, when Akari surveyed the same region, that source was gone from its original location. But at a position approximately 47.5 arc-minutes away, a shift equivalent to roughly 1.5 times the diameter of the full moon, an Akari source appeared, consistent in brightness and infrared color, with what Planet 9 would be expected to produce at a distance of roughly 500 to 700 astronomical units, or about 46 to 65 billion miles from the Sun. The brightness profile of both detections, measured at 65 and 90 microns, wavelengths in the far infrared, pointed to a body with a surface temperature between 28 and 53 kelvins, a world colder than liquid nitrogen, consistent with an ice giant slowly cooling at the far edge of the solar system, and the inferred mass, based on those infrared flux measurements, somewhere between 7 and 17 Earth masses, possibly greater than Neptune. But here is where the evidence deepens in an unexpected direction. The Akari satellite detected this candidate multiple times within a single day in June of 2006, but it was absent from observations taken 6 months later, consistent with what would be expected from an object moving along an orbital path, having shifted its position during that interval. Stationary background sources, galaxies, distant nebulae do not disappear from one observation and reappear slightly shifted in another. Moving solar system bodies do. The researchers were careful. They acknowledged explicitly that two detections separated by 23 years are not sufficient to confirm a full orbital solution. A planet must be observed at least 9 times across a linked arc to establish a confirmed Keplerian orbit, the characteristic elliptical path that all gravitationally bound solar system bodies follow. They also noted that other explanations, a faint background transient, coincidental positional alignment, could not yet be fully ruled out. But the convergence of evidence was striking enough that the authors described it as the most compelling single observational candidate the approach had yet produced. This is the point at which it becomes worth pausing to ask, what does it actually take for a single detection to qualify as a credible Planet 9 candidate, rather than just an interesting anomaly? Scientists apply a set of layered criteria. First, the brightness must match the predicted thermal output of a cold distant giant at the proposed distance, not just in one wavelength band, but across multiple infrared channels simultaneously. A background galaxy or galactic dust cloud produces a very different spectral signature than a cold planetary body. Second, the object must show motion consistent with orbital mechanics, the specific relationship between distance, orbital period, and rate of sky movement that Kepler's laws predict. An object 500 astronomical units away should move at a particular rate. Too fast, and it is a closer, unidentified asteroid. Too slow, and the geometry does not fit. Third, the candidate must be absent from positions it should have vacated and present at positions it should have reached across multiple independent surveys. Fourth, it must not appear in any of the known catalogues of stars, galaxies, brown dwarfs, or previously identified solar system bodies. The Fan et al. Candidate satisfies several of these criteria in a way that previous candidates did not. That is what distinguishes it. Not certainty, but a convergence of consistent signals across independent observations, filtered through rigorous elimination. And the next step, to move from compelling to confirmed, requires exactly the kind of follow-up observation that current technology can now, for the first time, genuinely provide. The research team specifically proposed that the Dark Energy Camera, DCAM, a powerful, wide-field optical instrument mounted on a 4-meter telescope in Chile, be used to attempt to redetect the candidate at its predicted current position. DCAM's sensitivity and field of view make it well suited to either confirm or rule out the object within a modest observing program. But there is a deeper complication. WISE, the all-sky infrared survey that ran between 2010 and 2011, did not detect this candidate. The team's explanation is straightforward. The planet, if real, would have moved from its 2006 position by the time WISE observed the region. Without knowing its precise orbit, it is currently impossible to calculate where the object would be in the WISE images. The absence is consistent with motion, but it is also consistent with the candidate being something else entirely. Without a confirmed trajectory, the silence of one survey cannot be used as either evidence for or against existence. This is the knife's edge that the entire Planet 9 search currently occupies. Not disconfirmed. Not confirmed. Living in the tension between a signal too consistent to dismiss and a dataset too sparse to declare certain. What makes this moment genuinely significant in the history of the search is not simply that one candidate has emerged. Candidates have emerged before. Earlier searches in IRAS data alone, conducted by British astronomer Michael Rowan Robinson in 2021, identified a potential detection at roughly 225 astronomical units, with an estimated mass of 3 to 5 Earth masses. That candidate remains unconfirmed and poorly constrained. What makes the current situation different is the convergence of multiple independent lines of evidence, the orbital clustering argument from Batygin and Brown, now updated through years of additional simulations, the independent archival detections from 2 separate surveys separated by 2 decades, and the arrival of instruments, Webb, Rubin, capable of resolving ambiguity in ways that no previous telescope could match. Something is out there, or something is not. The evidence, as it stands, does not resolve that question, but it sharpens it, and the way science sharpens a question is by asking it more carefully, not just where an object was seen, but what kind of world it might be, what forces shaped it, what its existence would mean for the history of the solar system we call home. Before we can fully evaluate what this candidate implies, we need to understand something more fundamental about the object being sought, not just where it might be, but what it might be, how a world of that size could have ended up at that distance, what its formation history might look like, and why its existence, if confirmed, would rewrite what we thought we understood about how our own solar system was assembled. To understand what Planet 9 might be, we first have to understand how the solar system was built, because its story is far more violent, far more chaotic, and far more unfinished than most people realize. We tend to think of our solar system as a settled, orderly place, 8 planets in neat, well-behaved orbits, the sun at the center, steady and ancient, everything in its place. But that picture, that sense of stable arrangement, is the end result of billions of years of catastrophic sorting. The solar system we see today is the survivor of collisions, ejections, and near misses that shaped everything from the tilt of the planets to the architecture of the outer solar system in ways scientists are still working to understand. And somewhere inside that story of chaos, perhaps central to it, may be the origin of a world we have never seen. 4.5 billion years ago, the sun had just ignited. Around it swirled a vast disk of gas and dust and rock, protoplanetary disk, from which every planet, moon and asteroid in our solar system eventually assembled. The process was not gentle. Planetary cores formed by accretion, meaning they grew by sweeping up smaller bodies in an unending succession of collisions. The early solar system was a demolition derby operating on geological timescales. Among the objects taking shape in this disk were the building blocks of the giant planets, the icy planetary cores that would eventually grow into Uranus and Neptune. The current scientific understanding, refined over decades of simulations, is that the early solar system likely contained not 4 giant planets, but 5. 5 planetary cores competing for material, jostling for orbital space, gravitationally interacting in a system that was not yet settled. The instability, when it came, was dramatic. Some cores were flung inward, others were scattered outward. In simulations of this process, 1 or 2 surplus cores typically end up ejected, either thrown entirely out of the solar system into interstellar space, or pushed to such extreme distances that they spend most of their existence in permanent isolation. Michael Brown put it plainly when he first proposed the Planet 9 hypothesis. There is no reason that there could not have been 5 cores rather than 4, he said. Planet 9 could represent that 5th core, and if it got too close to Jupiter or Saturn, it could have been ejected into its distant eccentric orbit. The ejection scenario is the most widely accepted formation pathway for Planet 9, and it works in a way that, once understood, feels almost inevitable. Early in the solar system's history, when the giant planets were still migrating and their orbital arrangement was shifting, a close encounter between a planetary core and one of the gas giants, most likely Jupiter or Saturn, would have delivered an enormous gravitational kick. The kind of kick that changes everything. A planet that passes close enough to Jupiter to receive that slingshot would not be destroyed, but its orbit would be drastically altered. A once circular inward orbit would become a long, wildly eccentric path, carrying the planet first outward to extreme distances, then swinging it back inward again, then outward once more for billions of years. But there is a problem with this scenario in its simplest form. A planet ejected violently by Jupiter would often be given enough velocity to escape the solar system entirely. What prevents the escape? Two proposed mechanisms: the gravitational tidal influence of other stars passing close to the early solar system as it was still embedded within its birth cluster of stars, or drag from the remnant gas of the solar nebula, the cloud of gas from which the Sun formed, which was still partially present during the early instability period. Either force could gradually reduce the eccentricity of the ejected planet's orbit and lift its closest approach to the Sun out of the range where it would continue to interact with the giant planets. The result? A stable, permanent orbit at the outer frontier. A study published in Nature Astronomy in May 2025, led by Andre Isidoro at Rice University and Nathan Kaib at the Planetary Science Institute, added compelling new support for this pathway. Using thousands of computer simulations of planetary systems embedded in realistic star cluster environments, they found that if the solar system underwent two specific instability phases, the growth of Uranus and Neptune and a later scattering event among the gas giants, there is up to a 40% probability that a Planet 9-like object could have been trapped in a wide, stable orbit. Not a certainty, but a remarkably high probability that makes the idea deeply plausible. If Planet 9 exists and its formation followed this path, the resulting world would be unlike anything in the inner solar system, but not entirely unlike anything in the known universe. Current models, based on its predicted mass of 5 to 10 times that of Earth, suggest a body most similar to a sub-Neptune or super-Earth, categories of planet that turn out to be extraordinarily common around other stars, but absent from our own 8-planet solar system. A world of 10 Earth masses would have a radius roughly 3.5 times that of Earth, about 23,000 kilometers across, compared to Earth's 6,378 kilometers. Not quite the size of Uranus or Neptune, but in the same family. Its likely composition, according to theoretical models, would include a hydrogen-helium atmosphere, an iron core, and a mantle of magnesium, silicate, and water ice, similar in broad structure to the ice giants we already know. But this world would be profoundly cold, profoundly dark. At its predicted distance from the Sun, the solar flux, the amount of energy arriving from the Sun would be reduced so dramatically that the surface would settle to a temperature of roughly 47 kelvins. 47 kelvins is minus 226 degrees Celsius, minus 375 degrees Fahrenheit, colder than any natural environment on Earth, colder than liquid nitrogen. In that temperature regime, the dominant thermal signature would come not from reflected sunlight, but from the slow, steady leaking of heat from the planet's original formation, primordial warmth, billions of years old, still faintly radiating outward into a void that will never warm it further. Picture what that world would look like from its surface. You are standing on a frozen plain of ancient ice, methane frost, water ice, rock. The sky above you is black and perfect, not twilight, not the bruised blue of high altitude, pure, undiluted darkness, scattered only with the same stars you would recognize from Earth, arranged exactly as they are now, because at these distances even the motion of a planet does not perceptibly shift the constellations, and there, among those stars, is the Sun, not a disk, not a source of warmth, just the brightest point of light in the sky, far brighter than any other star, but cold, distant, offering no heat you could detect with your hands. Scientists estimate that from Planet 9's predicted distance, the Sun would appear roughly 250,000 times fainter than it does from Earth. You could block it completely by holding up a pencil at arm's length. The entire inner solar system, Mercury, Venus, Earth, Mars, Jupiter, would be invisible without a telescope, compressed into a tiny ring of orbits around that single bright point. That is the darkness in which Planet 9 has existed, if it is real, for 4.5 billion years. Patient, unmeasured, unknown. To understand what we might expect from a world at these distances, it helps to look at what we have already found at the outer frontier, objects discovered not by prediction but by painstaking survey work, offering a glimpse of what the far solar system actually contains. Sedna was discovered in November 2003 by a team led by Mike Brown, Chad Trujillo, and David Rabinowitz, using the Samuel Oschin telescope at the Palomar Observatory. Its discovery was genuinely shocking. Sedna orbits the Sun on a path that carries it from roughly 76 astronomical units at its closest, already more than twice Neptune's distance, to about 937 astronomical units at its farthest. An orbit so elongated that Sedna spends only a tiny fraction of its nearly 12,600-year journey anywhere near the Sun. At its most distant, Sedna travels nearly as far as the predicted inner edge of the Oort cloud, a region astronomers had theorized existed but never directly observed. Sedna was about 1,000 kilometers, or 600 miles, across less than half the diameter of Pluto, already an extraordinary object, but far too small and far too close to be Planet 9. Far, far out, officially designated 2018 AG37, was discovered in January 2018 by Scott Shepard, David Tholen, and Chad Trujillo during a survey specifically aimed at hunting Planet 9. Confirmed in February 2021, Far Far Out was, at the time of its announcement, the most distant known object in the solar system, at 132 astronomical units from the Sun, roughly 12 billion miles or about 19 billion kilometers from home. Its orbit carries it out to an extraordinary 175 astronomical units at aphelion and back to just 27 astronomical units at perihelion, so elliptical that a single orbit takes roughly 1,000 years to complete. Its estimated size is about 400 kilometers, barely at the threshold of dwarf planet status. The astronomers who found it were direct about what it meant. Far Far Out, they said, was just the tip of the iceberg. Both Sedna and Far Far Out demonstrate something important. The outer solar system is not empty. Even before Planet 9's hypothetical location, the space beyond Neptune contains worlds. Small ones, yes, but genuine planetary bodies on extraordinary elongated orbits. They are the visible members of a population that almost certainly contains many more objects we have not yet found. Planet 9, if real, would be the largest and most distant of them all, a world that belongs to a class of solar system object that until recently we did not know existed. Here is where the story takes an unexpected turn, and scientific honesty demands we follow it. In September 2019, astronomers Jakob Scholz of Durham University in the United Kingdom and James Unwin of the University of Illinois proposed something genuinely startling: the gravitational anomalies in the outer solar system that everyone was attributing to a hidden planet might not be caused by a planet at all. They might be caused by a primordial black hole. A primordial black hole is not the kind of black hole formed when a massive star collapses at the end of its life, the dramatic stellar mass objects that have captured scientific and popular imagination. A primordial black hole is something older and stranger. These are hypothetical objects, thought to have formed in the first fraction of a second after the Big Bang, when tiny regions of the early universe became so dense that they collapsed directly into black holes, not from dying stars, but from the raw turbulence of the newborn cosmos. If they exist in the right mass range, and Scholz and Unwin argue that some should, a primordial black hole of 5 to 10 Earth masses would be physically tiny, about the size of a grapefruit, small enough to hold in your hands, massive enough, compressed into that tiny volume, to exert the same gravitational influence as a world the size of a small planet. Scholz and Unwin calculated that the probability of the Sun capturing a wandering primordial black hole into orbit during the early solar system's turbulent formation phase, when encounters with other objects were far more frequent, is comparable to the probability of capturing a free-floating rogue planet. Comparable, not identical, but not negligibly small either. The published paper, which appeared in Physical Review Letters, proposed a detection method. A primordial black hole, unlike a planet, would emit no infrared radiation from a warm surface, but it would accumulate a cloud of dark matter around it, and that dark matter, if it annihilates, could produce detectable signals in X-rays, gamma rays, and other high-energy radiation. Signals that would be fundamentally different from anything a planet would produce. Konstantin Batygin, who has dedicated years of his career to the Planet 9 hypothesis, acknowledged the idea with characteristic precision. While it is possible for Planet 9 to be a primordial black hole, there is currently not enough evidence to make this idea more plausible than any other alternative. Mike Brown put it more bluntly, "All we know is that there is a 6 Earth mass something out there, and we don't know what the something is." He paused to acknowledge, "The physics doesn't care. If it has the right mass and the right orbit, the gravitational effects are identical regardless of whether it is a planet, a primordial black hole, or anything else." That uncertainty is not a weakness in the story. It is the honest shape of where science currently stands. Whether it is a planet or something stranger, the existence of a 5 to 10 Earth mass body at the solar system's outer edge would resolve one of the most persistent puzzles in planetary science. Surveys of planets around other stars have revealed that the most common type of planet in the galaxy, by a wide margin, is the super-Earth or sub-Neptune. Worlds ranging from 1.5 to 3.5 times the size of Earth, composed of varying mixtures of rock, water, ice, and gas. They orbit billions of stars across the Milky Way. They appear to be a natural, default outcome of planetary formation, and yet our own solar system contains none of them. Between Earth and Neptune, a factor of 17 in size, there is simply nothing, a gap that makes our solar system statistically unusual. Planet 9, if real, would fill that gap. Not where the other known planets are, but confirmation of its existence would suggest that our solar system produced a super-Earth, attempted to retain it, and failed. The planet was scattered outward before it could fully form. What we have been calling a missing planet was not missing at all. It was simply exiled, sent into a long, dark ellipse at the solar system's edge, where it has orbited in silence for billions of years, while the inner system settled into the orderly arrangement we now observe and call home. But none of this is settled. The formation scenarios are compelling, the physical models are internally consistent. The comparison to distant objects like Sedna and far, far out makes the existence of Planet 9 feel plausible rather than exotic. And yet, for every scientist who finds the hypothesis persuasive, there is another who finds the evidence insufficient, who looks at the same data and sees not a hidden planet, but the fingerprint of incomplete surveys and statistical noise. That disagreement is not a distraction from the science. It is the science, and it deserves to be examined directly, because the arguments against Planet 9's existence are serious, sourced, and made by serious people. Understanding those arguments does not weaken the case for Planet 9. It clarifies exactly what kind of evidence would be needed to resolve the question once and for all. The arguments against Planet 9's existence are not made by people who haven't looked at the data. They are made by people who have looked at exactly the same data and reached entirely opposite conclusions. That distinction matters. When a scientific hypothesis is challenged not by ignorance but by rigorous competing analysis from credentialed researchers at major institutions, the disagreement is not a sign that science has failed. This is what science genuinely looks like. Not a parade of elegant confirmations, but a sustained, disciplined argument between people who take the same evidence seriously and arrive at different places. Nowhere in the Planet 9 story is this more apparent than in the central question the entire hypothesis rests on: whether the clustering of distant solar system objects is real, a genuine gravitational signature, or an artifact of the limits of human observation. To understand why the counter-arguments are serious, we need to hold the original claim clearly in mind. Batygin and Brown's hypothesis does not rest on directly observing a planet. It rests on a statistical pattern in the orbits of a small group of extreme trans-Neptunian objects, icy bodies whose orbits extend beyond 250 astronomical units from the Sun, orbiting the Sun on paths so elongated they spend most of their time in regions so distant we cannot even see them. These objects, the argument goes, are aligned. They cluster in the same direction, with similar orbital tilts, in a way that, according to Batygin and Brown's calculations, has only a very small probability of arising by chance. Konstantin Batygin has been direct about the weight he places on this. He has described 5 separate lines of observational evidence pointing toward Planet 9, including the orbital clustering, the existence of objects tilted nearly perpendicular to the solar plane, the presence of highly inclined and retrograde distant objects, the detached orbits of Sedna-type bodies, and what may be a small residual tilt of the Sun itself relative to the planetary plane. If you were to remove this explanation and imagine Planet 9 does not exist, he said, then you generate more problems than you solve. All of a sudden, you have 5 different puzzles, and you must come up with 5 different theories to explain them. That is a compelling argument. But the counter-argument begins with a deceptively simple question. Are those 5 lines of evidence actually independent, or do they all trace back to the same potentially flawed dataset? The most powerful scientific challenge to Planet 9 does not dispute the mathematics of gravitational clustering. It disputes something more fundamental: whether the objects used to demonstrate that clustering constitute a representative sample of the outer solar system, or whether they are a distorted snapshot, shaped by the limitations of the telescopes that found them. This is what astronomers call observational bias, the systematic tendency to find things not where they actually are, but where we were looking. Samantha Lawler, an astronomer at the University of Regina in Canada, who has spent years studying distant Kuiper Belt objects, articulates the problem with clarity. Finding extreme trans-Neptunian objects is not like finding a star. These objects are faint, small, and spend the vast majority of their orbital time in regions so far from the Sun that they are essentially invisible. The only time they can be detected is during their brief approach to the inner solar system, when they swing close enough to reflect a detectable amount of sunlight. And even then, the detection depends critically on where telescopes are pointed, what time of year observations are made, and whether the Milky Way's dense star field is blocking the background. Every survey has biases, Lawler says. Some are aware of them, some are not. The implication she is drawing is significant. If the surveys that discovered the clustered extreme trans-Neptunian objects all happen to look at the same regions of the sky, for reasons of scheduling, weather, or telescope positioning, then the apparent alignment of those objects' orbits might say nothing about the solar system's structure. It might only say something about where human beings happen to point their instruments. In 2017, a study led by Corey Shankman and colleagues, including Lawler, from the Outer Solar System Origin Survey, or OSOS, published a direct challenge to the Planet 9 hypothesis. OSOS was a major 5-year program using the Canada-France-Hawaii telescope, designed from the outset to carefully document and account for its own observational biases. The survey ran from 2013 to 2017 and discovered more than 800 new trans-Neptunian objects, nearly doubling the number of known objects with well-measured orbits in a single program. 800 objects. Compare that to the original 6, and later 14, objects that Batygin and Brown had used as the foundation of the clustering argument. 8 of those OSOS objects had semi-major axes, large enough to fall within the category used to argue for Planet 9. When Shankman and the team analysed their orbital directions, accounting carefully for the known survey biases, they found no evidence of clustering. The orbital distribution of those 8 objects was fully consistent with a uniform angular distribution, objects pointing in all directions, as you would expect if no hidden planet was steering them. Lawler's assessment was pointed. Planet 9, as proposed, does not hold up to detailed observations. In 2020, the Dark Energy Survey reached similar conclusions, discovering over 300 additional trans-Neptunian objects with no detected clustering. So here is the paradox. The original evidence for Planet 9 was based on roughly 14 objects. Two major independent surveys covering 800 and 300 objects respectively found no clustering when their biases were properly accounted for. How can the same solar system yield such different conclusions? Several substantive alternatives to Planet 9 have been proposed by researchers working in published peer-reviewed literature. Each offers a different explanation for the orbital anomalies that spark the hypothesis in the first place. One alternative, Neptune's migration. Mathematical simulations, including work Lawler and the OSOS team have published, show that the highly elliptical and tilted orbits throughout the Kuiper belt can be explained entirely by Neptune having originally formed a few astronomical units closer to the Sun and migrated outward over time. That outward migration, dragging and scattering small bodies through resonance effects, produced a Kuiper belt whose structure we are still decoding today. On this model, no. Additional planet is needed to explain most of what we observe. A second alternative, proposed in a 2019 paper published in the Astronomical Journal, the collective self-gravity of the trans-Neptunian disk itself. The idea is that a sufficiently massive extended disk of icy objects beyond Neptune could, through the combined gravitational interactions of all its members, shepherd smaller orbits into apparent alignment without any single massive planet being responsible, a disk rather than a point mass, as the sculptor. A third possibility, the apparent clustering of the original 6 objects was never statistically significant in the first place. With only 6 initial data points, and later 14, the clustering falls squarely within what statisticians call small number statistics. A small sample can easily appear clustered by chance, even if the underlying distribution is entirely uniform. Kevin Napier of the University of Michigan led a careful study, combining data from 3 different surveys, and found that 14 extreme trans-Neptunian objects showed no significant clustering once all 3 surveys' biases were accounted for together. And then, in 2025, came 2 discoveries that pushed the debate in a new direction. In May 2025, astronomers announced the confirmation of a distant object designated 2017 OF201, a dwarf planet candidate roughly 500 to 900 kilometers across, with an extraordinary orbit stretching from about 45 astronomical units, at its closest to an astonishing 1,610 astronomical units at its farthest. Its orbit does not align with the other extreme trans-Neptunian objects used to argue for Planet 9. 2 months later, in July 2025, a team led by Ying-Tung Chen of the Academia Sinica Institute of Astronomy and Astrophysics in Taiwan announced the discovery of 2023 KQ-14, nicknamed Ammonite, only the 4th, known member of the rare Sednoid class. Sednoids are among the most distant, isolated objects in the solar system, their orbits so extreme they are never influenced by Neptune. Ammonite has a perihelion of about 66 astronomical units, a semi-major axis of about 252 astronomical units, and an orbit that has remained stable for at least 4.5 billion years. But here is what struck astronomers immediately. Ammonite's orbit points in the opposite direction from the other 3 known Sednoids, Sedna, 2012 VP113, and Leliakuhonua. The entire clustering argument was built on the observation that Sednoids and extreme trans-Neptunian objects are grouped on one side of the solar system. Ammonite is on the other side. If a hidden planet were shepherding these objects into a common alignment, why is the newest one aligned differently? Yukun Huang of the National Astronomical Observatory of Japan said directly, "The fact that 2023 KQ-14's current orbit, does not align with those of the other three sednoids, lowers the likelihood of the Planet 9 hypothesis. But, and this is what makes the science genuinely difficult, the discovery does not rule it out. Some simulations suggest that if Planet 9 exists but orbits even further from the Sun than currently predicted, around 500 astronomical units, Ammonite's orbit could remain stable. The discovery of Ammonite may not kill Planet 9, it may simply push it further away. Batygin and Brown have not been passive observers of this debate. In 2021, they published a reanalysis of the clustering evidence, specifically designed to account for observational biases in all the known surveys simultaneously. After that rigorous correction, they concluded that the orbital clustering remains significant at a 99.6% confidence level. 99.6%. That sounds definitive, but in a field where only about 14 well-characterized, extreme trans-Neptunian objects exist, any statistical statement carries large uncertainties. Lawler argues that with such small sample sizes, even rigorous bias correction cannot produce the kind of statistical confidence that would normally justify a discovery claim. The dispute, at its core, is not about the mathematics. Both sides can do the calculations. The dispute is about whether 14 objects, now challenged by Ammonite and 2017 OF201, constitute a sample large enough to support the conclusions being drawn from them. Fred Adams of the University of Michigan has assessed that enough data will accumulate at the current rate of discovery and with upcoming surveys to either confirm Planet 9's existence or rule it out by approximately 2035. That is not a long time in human terms. In cosmic terms, it is barely a breath. Sitting with this debate long enough, something becomes clear that is easy to miss in the noise of the argument itself. Both sides are doing exactly what science is supposed to do. Batygin and Brown identified a genuine statistical anomaly, built a rigorous mathematical model, published their predictions, and then continued to refine and defend them as new data arrived. Lawler and the OSSOS team identified a genuine methodological concern, built a careful survey designed to address it, published their findings, and argued their position with equal rigor. Neither side has fabricated data. Neither side has ignored the other's arguments. Both have updated their positions as new evidence arrived. This is the scientific method functioning correctly, messy, contested, productive, unresolved. The viewer watching this debate from the outside often wants a verdict. Planet 9 exists, or it does not. The honest answer is that science does not yet have one. What it has is a genuine tension between two serious positions, a growing data set that has so far failed to resolve it, and a converging set of instruments that may finally be capable of ending the argument once and for all. The question is not merely whether Planet 9 is real, the question is whether our current methods of cataloguing the outer solar system are complete enough to trust the patterns we think we see. And that is a deeper, more important question, one that would need answering even if Planet 9 never existed. All of this brings us to a threshold moment in the history of this search. Not a conclusion, but a genuine turning point, because everything examined so far, the archival candidates, the infrared searches, the bias debates, the mathematical models, the new discoveries, represents the accumulated evidence of a science working at the edges of what current technology can answer. What changes that calculation is not more argument. More argument has been available for nearly a decade. What changes it is data, specifically the kind of systematic, large-scale, bias-corrected data that would allow astronomers to either confirm or definitively rule out the clustering that started this entire story. The kind of data that the Vera C. Rubin Observatory is now positioned to deliver. The kind of data that, combined with targeted Webb observations of the most promising candidates, might within the next few years either produce a confirmed detection or a systematic null result that narrows the hypothesis to the point of near extinction. We are at the edge of that moment, and understanding what the next decade of searching might actually look like, what it would mean for Planet 9 to be found, and what it would mean for it not to be, requires stepping back from the debate and asking the larger question: what is the resolution of this story going to change about how we understand our place in the solar system? Science rarely announces in advance that it is about to close a question, but in the Planet 9 search, for the first time in the nearly decade-long history of this debate, the instruments arriving online are powerful enough and systematic enough to actually do it. Not to confirm the hypothesis with certainty, not to rule it out with finality on day one, but to gather, over the course of a few years, data of a quality so vastly superior to anything previously collected that the ambiguity at the centre of this story will be forced, one way or another, to resolve. That is an extraordinary place for a scientific debate to reach, and we are in it right now. The fundamental reason Planet 9 remains undetected after nearly 10 years of active searching is not a failure of effort or intelligence. The scientific community has mounted one of the most resourceful and methodical planetary searches in history. The reason is simpler and more structural. No survey available since 2016 has been both wide enough and deep enough, while simultaneously being well characterized enough in its observational biases to either confirm or refute the clustering evidence that started the hypothesis. WISE surveyed the whole sky in infrared, but lacked the sensitivity to detect Planet 9 at the far end of its predicted orbit. Existing ground-based surveys cover broad regions, but are hampered by limited aperture, seasonal gaps, and incomplete bias characterization. The Outer Solar System Origin Survey was carefully calibrated, but targeted only specific patches of sky, not the full sphere. The Zwicky Transient Facility has searched 3 years of data and ruled out approximately 56% of the predicted parameter space, but 56% is not enough. What the search needs is a survey that scans the entire accessible sky repeatedly, deeply, and with mathematically known detection biases, so that absence of detection in a given region genuinely means the planet is not there, rather than simply meaning the telescope wasn't looking properly. That survey has now begun. The Vera C. Rubin Observatory began generating its first science alerts in February 2026. The full legacy survey of space and time, LSST, is now underway, and over the coming decade it will revisit approximately 18,000 square degrees of the southern sky, or roughly half the entire celestial sphere, with an average of around 825 individual visits to each patch over 10 years. The key to why this matters for Planet 9 is not the single night sensitivity of each image. By itself, one Rubin image of a distant planetary candidate would show only a faint dot indistinguishable from thousands of background objects. What transforms those individual images into a discovery engine is time, repetition. The observatory's automated systems compare every new image to all previous images of the same sky region and flag anything that has moved or changed. Every few nights, the same patch of sky is observed again and again. Month after month, year after year, a picture of every slowly drifting object in the southern sky gradually assembles itself. Picture the difference between a single photograph of a busy street corner taken once and a time-lapse filmed over an entire year. The photograph freezes a single moment, every person, every car indistinguishable from background objects in the city. The time-lapse reveals everything that moved, the rhythms of traffic, the patterns of pedestrians, the seasonal change in light. Rubin is building that 10-year time-lapse for half the southern sky, and a planet, drifting slowly but measurably against the fixed backdrop of stars, would reveal itself in exactly this way, not by being bright, but by being unmistakably, undeniably in motion. Scott Shepard of the Carnegie Institution for Science, one of the researchers who first identified the orbital clustering that sparked the Planet 9 hypothesis, said it directly. Vera Rubin is our best bet to find it in the next few years probably. It's going to turn over more rocks than anyone has turned over before. His estimate, accounting for the considerable uncertainties in Planet 9's exact size and reflectivity, is that if the planet exists within the detection range of the survey, Rubin has a 70 to 80% chance of finding it. Mike Brown put his personal position plainly. If we find something moving out around 500 to 600 astronomical units, it will be Planet 9. Right now, as you sit wherever you are reading or listening to this, Rubin's 3-mirror telescope on Cerro Pachon is rotating in the dark above northern Chile. Every few seconds, its 3.2 gigapixel camera captures a new patch of sky. Within 60 seconds of each observation, automated processing pipelines are comparing that image to the accumulated archive and generating alerts for anything that has moved, brightened, or changed. Up to 10 million such alerts per night, flowing out to astronomers around the world in near real time. The first year of survey data alone, when released in the first full data release planned for around 2028, is expected to transform the known catalogue of outer solar system objects, increasing the number of well-characterized extreme trans-Neptunian objects by an order of magnitude or more. From roughly 14 objects that spark this entire decade of debate to potentially hundreds of new objects, each with a precisely determined orbit. That is the difference between trying to understand the structure of a forest by looking at 6 trees and finally being able to see the entire canopy from above. But Rubin alone may not be the complete answer, and here is where the relationship between ground-based survey telescopes and space-based precision instruments becomes genuinely powerful. Rubin is optimized for breadth. Its extraordinary wide field of view, covering 9.6 square degrees in a single image, an area roughly equivalent to 45 full moons side by side, allows it to scan vast stretches of sky efficiently. What Rubin sacrifices for that width is depth in certain wavelengths. In particular, Rubin operates in optical and near-infrared light. A planet in the coldest, most distant part of its predicted orbit, a planet emitting its faint warmth primarily at mid-infrared wavelengths, would be at the very edge of Rubin's sensitivity and might slip below its detection threshold. This is precisely where Webb enters the picture as a complementary instrument. The relationship works as follows. Rubin identifies moving candidates. Any slow-drifting point source that appears in the Rubin data. Anything that shifts its position consistently over months and follows the kind of gentle arc that an outer solar system orbit would produce, becomes a target for all follow-up, pointed follow-up, the kind that Webb can provide with its extraordinary mid-infrared sensitivity, staring at a small patch of sky for hours, reaching depths that no survey telescope can match. If Rubin finds the motion, Webb can confirm the cold infrared signature that would distinguish a distant planetary body from any closer, warmer imposter. Additional synergy comes from the world's largest ground-based telescopes, Keck Observatory, the Subaru telescope, the Very Large Telescope in Chile, which can provide spectroscopy and astrometry precise enough to lock down an orbital solution from a handful of confirmed positions. The combination of these resources means that if a candidate appears in Rubin data, the global astronomical community has the tools to characterize it rapidly. The era of waiting years for follow-up confirmation is over. There is one more ingredient in the search that deserves its own moment. The people who are not professional astronomers and yet have contributed meaningfully to this story. Since 2017, a project called Backyard Worlds, Planet 9 has been running on the Zooniverse platform, a citizen science website that channels public volunteer effort toward real scientific problems. The project, led by Mark Kuchner of NASA's Goddard Space Flight Center, asked volunteers to look through flipbook-style animations of infrared images from the WISE satellite and identify slowly moving objects that automated systems might miss. The human visual system, it turns out, is remarkably good at pattern recognition in precisely the kind of noisy, artifact-filled images that confound machine classifiers. More than 85,000 volunteers worldwide have participated. Their collective effort has discovered more than 3,800 new brown dwarfs, objects too small to be stars, too large to be planets, lurking close to our solar system. more than 40 citizen scientists became co-authors on published scientific papers from the project. In June 2023, the project team launched an AI-enhanced companion called Backyard Worlds, Cool Neighbors, which uses machine learning algorithms developed in part by a volunteer software engineer named Dan Caselden to pre-select the regions of sky most likely to contain objects of interest. Volunteers then inspect those pre-selected regions, focusing their effort where it is most likely to pay off. The result was nearly 3 times the classification rate compared to the original non-AI project. The human eye and the machine learning algorithm working together outperform either one alone. Neither technology is the answer. The combination is. When Rubin's data begins flowing in volume, citizen science initiatives similar to Backyard Worlds may be adapted to help process the unprecedented torrent of new outer solar system candidates, providing a human verification layer for objects that automated pipelines flag, but struggle to cleanly classify. Fred Adams of the University of Michigan has published an assessment that, at the current rate of new outer solar system discoveries, and with upcoming survey capabilities accounted for, enough data will have accumulated by approximately 2035 to either pinpoint Planet 9's position or effectively rule out its existence in its currently predicted form. 2035. That is less than 10 years from now, within the professional careers of the astronomers currently arguing about it within a generation. A question that has haunted planetary science since 2016 may have a genuine answer, one way or the other, within the lifetime of the people reading these words, and the nature of that answer matters enormously. Here is where scientific honesty demands we examine both outcomes with equal care. If Rubin completes its 10-year survey, and Planet 9 is not found within the parameter space that has been searched, if no slowly drifting point source at 500 to 700 astronomical units turns up in the data, that absence carries genuine meaning. A non-detection does not simply leave the hypothesis unchanged. A systematic, well-characterized non-detection over most of the accessible sky would severely constrain the classical Planet 9 hypothesis. Any surviving version of the planet would have to be darker than expected, farther than predicted, or smaller than current models suggest. Each constraint narrows the remaining possibility space. Samantha Lawler and other skeptics have argued this is the most likely outcome, that as the sample of extreme trans-Neptunian objects grows from 14 to hundreds, the apparent clustering will dissolve into the statistical noise it may always have been, and the anomaly that inspired the hypothesis will simply disappear. Batygin and Brown have argued the opposite, that the clustering is robust, that 5 independent dynamical signatures all point to the same source, and that a large systematic survey will confirm rather than refute them. Both positions are held by serious scientists with serious arguments. Both cannot be right, and within the decade, we will likely know which position the data actually supports. A non-detection would be genuinely valuable, even if humbling. It would transform our understanding of the outer solar system's bias problem, proving conclusively that the apparent clustering of extreme trans-Neptunian objects arose from incomplete asymmetric surveys rather than a hidden gravitational source. That would be an important scientific finding, not a failure. Eliminating a hypothesis is not the same as losing a search. It is the same as gaining clarity. But suppose the answer goes the other way. Suppose Rubin data, in its first few years of operation, produces a drifting point source at 500 astronomical units, and Webb confirms a cold infrared signature consistent with an ice giant. Suppose the orbit is locked down. Suppose the discovery announcement is made. What changes? Not just the planet count, not just the solar system map. What changes is something deeper, the story we tell ourselves about where our solar system fits in the galaxy, how our planets were assembled, and what the arrangement we call home actually represents. The discovery of a 5th giant planet, exiled to the outer darkness billions of years ago, would rewrite the origin narrative of the solar system itself, and illuminate what our system's formation has in common with the billions of planetary systems now being discovered around other stars. The search has always been about more than finding a single object. Tracing one planet's long orbit brings us back to the very beginning of this story, to the question of what it means to live inside a solar system that may be older, stranger, and more eventful in its history than anything we previously imagined. And that question, what the existence or non-existence of Planet 9 finally tells us about our place in the cosmos, opens into the largest perspective of all. The search for Planet 9 has always been, at its surface, about a single object, a world, a mass, a predicted orbit, a candidate infrared signal in old survey data. The question, is it there or not, feels specific, concrete, almost simple. But tracing this story all the way through, from Percival Lowell's 19th century calculations to Batygin and Brown's 2016 hypothesis, to the candidates turning up in far infrared archives, to the scientific debate now converging on the most powerful instruments ever built, something larger has quietly accumulated. Something that was there from the beginning, but is only visible from here, at the end. The search for Planet 9 is not just a story about whether our solar system has 8 planets or 9. It is a story about what our solar system represents in the context of the galaxy, about whether its architecture is ordinary or exceptional, about what the invisible members of a planetary system say about the history that shaped it, and about what it means as thinking, measuring, searching creatures to live inside a universe where most of the important things remain just out of reach. To understand what is at stake in the Planet 9 story, it helps to step outside our solar system for a moment and see it through the same lens astronomers use when studying planetary systems around other stars. In the past 3 decades, the Kepler Space Telescope and TESS, the Transiting Exoplanet Survey satellite, have catalogued thousands of confirmed planets orbiting distant stars. The picture that has emerged from that catalogue is humbling. The most common type of planet in the galaxy is not a giant gas world like Jupiter or Saturn, nor is it a rocky world like Earth or Mars. The most common class of planet, confirmed by observation after observation, is a world somewhere between Earth and Neptune in size, commonly called a super-Earth or sub-Neptune, worlds between 1.5 and 4 times off the diameter of Earth, between a few and 10 times the mass of our planet. These worlds orbit billions of stars across the Milky Way in vast numbers. As soon as astronomers had instruments sensitive enough to find them, they appeared everywhere. As soon as we had the technological capability to find these planets, we started finding them in vast numbers, said Eliza Kempton, an astrophysicist who studies exoplanet atmospheres. That tells us they are intrinsically very common, and yet our own solar system contains none of them. Between Mars and Neptune, a factor of 17 in planetary size, nothing exists. The gap is real. Our solar system, by the dominant standard of the galaxy, is missing its most common type of planet. Planet 9, if it exists, fills that gap. Not in the expected position, not in the inner or middle solar system, but at the extreme outer edge, exiled, ancient, orbiting in silence at distances that make it functionally invisible to all conventional search methods. The discovery would not just add a number to the planet count, it would connect our solar system to the broader galactic population in a way that currently makes no sense. We would no longer be a planetary system anomalously lacking a super-Earth. We would be a planetary system that had one, and lost it, and here the story opens into something even larger. Planet 9, if real, did not end up at the outer edge of our solar system by accident. The ejection scenario that best explains its current position is rooted in a chaotic early solar system that scattered planetary cores the way a storm scatters leaves, most lost forever to interstellar space, but a few caught in wide, stable orbits by gravitational fortune. The planets that were not caught, the ones that escaped entirely, are now what astronomers call free-floating planets, or rogue worlds. Planets that orbit no star, worlds drifting alone through the dark between stellar systems, cold and invisible, traveling the galaxy without destination. Scientists estimate these objects vastly outnumber the planets we know. A 9-year gravitational microlensing survey conducted by the Microlensing Observations in Astrophysics team, announced in 2023, estimated that our galaxy may be home to 20 times more rogue planets than stars. With at least 100 billion stars in the Milky Way, that suggests roughly 2 trillion free-floating worlds drifting alone through interstellar space. 2 trillion. If you counted one rogue planet per second without stopping, not sleeping, not pausing, it would take more than 63,000 years to reach that number. Longer than all of recorded human civilization by a factor of more than 6. These are not hypothetical objects. Astronomers have already confirmed several of them using microlensing, a technique where a planet's gravity bends and briefly amplifies the light of a background star as it passes in front. The events are fleeting, measured in hours or days, but they are real. Rogue planets exist in numbers that appear to dwarf the planet's orbiting stars. The galaxy is flooded with them, ancient refugees from planetary systems that did not keep them. Planet 9 may simply be a rogue planet that was caught, a world that nearly escaped but was held by our sun's gravity at the last moment, settling into its extraordinary orbit. If this is what happened, then Planet 9 is not an anomaly. It is a connection, a thread linking our solar system to the broader galactic community of worlds, most of which travel alone. Picture the moment of discovery, not the announcement, the scientific moment before the announcement, when Rubin's automated system, or a Webb follow-up, or a researcher reviewing archival infrared data flags a slowly drifting point source at 500 astronomical units, and the measurements begin to converge on a Keplerian orbit, and the orbital period locks in at 10,000 years, and the infrared signature aligns with the predicted thermal emission of a cold, distant ice giant. What changes in that moment? The solar system gains its 5th largest planet, not 5th from the Sun, 5th in mass, larger than all known worlds between Earth and Neptune. A classification revision follows. New orbital simulations will be required to incorporate a gravitational body of that mass at that distance into every solar system model ever constructed. The clustering evidence that has been disputed for a decade collapses from hypothesis to fact. The 5 independent lines of dynamical evidence Batygin listed crystallize from argument into confirmation. Formation models of the early solar system gain their missing piece. The connection to exoplanet statistics becomes explicit. Our solar system's architecture is now understood, not as a system that lacked a super-Earth, but as a system that produced one, ejected it to the outer frontier, and held it there across billions of years of orbital evolution. The solar system is normal after all, uncommon in its arrangement perhaps, but normal in its history, normal in its violence, normal in the chaos of its formation. And for exoplanet science more broadly, the discovery would provide the first confirmed case within our own solar system of a wide orbit giant formed through ejection. Exactly the type of object that formation models predict should exist around many stars, but that has been extraordinarily difficult to confirm from first principles. Planet 9, found in our own backyard, would be the anchor observation for an entire class of planetary theory. But suppose Rubin's decade-long survey concludes without detection. Suppose Webb's targeted follow-up of the most promising archival candidates produces only dead ends. Suppose the data accumulates to 2,000 extreme trans-Neptunian objects, and their orbits distribute uniformly in every direction, with no clustering, no preferred, alignment, no gravitational signature pointing toward an unseen world. What does science do with that? Something honest and important. It acknowledges that the pattern that launched a decade of searching was real in the sense that it was observed, but was a product of incomplete data, not of a hidden planet, and it demonstrates, with a clarity that has rarely been achieved on such a long-running question, the specific mechanism by which observational bias can masquerade as cosmic structure, the way that gaps in our surveys, seasonal, geographic, optical, can shape apparent patterns that look, at first, exactly like the fingerprint of something unseen. That would be a genuinely valuable result, not a failure, a correction, a demonstration of the self-healing capacity of science, its ability to accumulate enough data to see past the distortions in its own earlier measurements. We would have learned something specific and important about the relationship between incomplete surveys and apparent clustering, something that would protect future researchers from similar errors in other contexts, and the outer solar system would remain not empty but unexplored, full of objects we have not yet found, histories we have not yet read, structures we have not yet mapped. With or without Planet 9, Rubin's decade of observation will transform what we know about the architecture of our solar system's outer regions. That transformation will happen regardless of what the search ultimately finds. We have travelled a long way together in this story. From Percival Lowell calculating in the dark to Clyde Tombaugh, at a blink comparator to Batygin and Brown, running simulations and arriving at a number they could not ignore. From Wise scanning the infrared sky to Webb, staring at cold, distant, faint things with a clarity nothing before it could reach. From an archival IRAS detection and an Akari source exactly where Planet 9 should have moved over 23 years, to the Rubin Observatory now scanning the southern sky every few nights, building a 10-year time-lapse of the outermost reaches of our cosmic neighbourhood. Sit with that for a moment. Not the excitement of discovery, just the magnitude of the patience it takes. This is one of the things science does that nothing else in human experience quite matches. It is capable of holding a question open with full intellectual honesty across decades, not pretending to know the answer, not collapsing the uncertainty prematurely, staying with the discomfort of not knowing because not knowing, pursued carefully, is the only path toward actually finding out. At the very start of this story, the first thing we said was this: something is moving at the edge of our solar system. We cannot see it. No telescope has ever captured its light. Stand here now, after everything we have learned, and feel how different that sentence sounds. Something is moving at the edge of our solar system. Not a ghost, not a fantasy. A gravitational signal, measured, debated, challenged, partially confirmed, not yet resolved, pointing toward an object that formed in the same disk of gas and dust that made the Earth, the Moon, Jupiter, every planet we have ever known. An object that was flung outward by a gravitational encounter billions of years ago, before the solar system had settled into its current form, and has been orbiting in the outer darkness ever since. An object whose existence, or non-existence, sits at the intersection of observational astronomy, planetary formation theory, and the deep question of what kind of system we actually live in. Something is moving, and what that something is, planet, shadow, ancient refugee, or statistical ghost, is what the next 10 years of human observation will decide. The unseen universe is not a failure of science. The unseen universe is the frontier science has always moved toward, carefully, persistently, with instruments built by human hands and minds reaching into depths that no instinct prepared us to reach. We did not evolve to detect infrared radiation at 50 astronomical units. We did not evolve to read gravitational signatures in orbital alignments, separated by hundreds of years of accumulated observation. We did not evolve to hold a question open for a decade and still follow the evidence wherever it leads. And yet here we are, doing all of it, building the instruments that extend our senses past every limit evolution gave us, writing the algorithms that find motion in data sets too large to read by eye, assembling the global collaborations, professional astronomers, citizen scientists, software engineers, telescope operators, whose collective effort is making the outer solar system legible for the first time. The shadow at the edge of our solar system is either real or it is not. We are in the process of finding out. That process, this slow, disciplined, patient, extraordinary act of looking, may be the most distinctly human thing we do. Not the discovery at the end of it. The looking itself. Something is moving, and we are the creatures who noticed. There is something quietly extraordinary about a species that looks at the edge of its own solar system and says, "We are not finished yet." Not because we need to be. Not because anyone is asking us to. Simply because the question exists, and we are the kind of creature that cannot leave a question alone. You are that kind of creature. The fact that you are here at the end of something this long and this uncertain tells me that, and I want you to know that matters to me more than any view count ever could. Thank you for your time, for your patience, for caring about something this far away. If this felt like something worth sharing, if it reminded you why the universe is still worth paying attention to, please like this video and subscribe. It is how I keep doing this work, and there is so much more I want to explore with you. And maybe that is the most human thing of all. Not the discovery, not the answer, but the willingness to sit with the uncertainty, to keep the question alive, to look at the dark and feel something instead of nothing. The universe keeps its secrets. We keep asking anyway.